Yeah, okay, I think we're on. Hello and welcome everyone to another episode of the AI co-learning program. I'm your host, Bruce, and it's great to have you all with us again today. In this session, we'll explore a rapidly evolving topic at the frontier of AI systems, LLM agents, skills, and OpenClaw. So as large language models move towards agent-based systems, we're beginning to see new paradigms emerge, where models can plan, collaborate, and continuously require new skills. So today's session is a bit special. We have four distinguished speakers, each bringing a unique perspective from research and industry. We'll begin with three individual talks. Each speaker will share their insights, followed by a short Q&A session with the audience. And after the individual talks, we'll move into a panel discussion, which will be moderated and led by Dr. Yuxi Li. Finally, we open the floor for live audience questions, so feel free to drop your questions in the live chat throughout the session. With that, let's get started with our first speaker. Please join in welcoming Dr. Gu Gao.
Hello, everyone. My name is Rujun Gao. I'm the founder and CEO of In Canada AI. In Canada AI, it's a AI-powered platform that we build for connect every teacher and learning. We help teachers to teach better and also deliver and distribute personalized learning for every student at scale. Okay, now let me share my screen. I can start my talk. Okay. If it's the screen share is okay, I can start it now.
Yes, it's okay.
Okay. Hi everyone. Today I'll be discussing enterprise RAG to agentic workflows and also some lessons learned from In Canada AI. This presentation will be cover four parts: enterprise RAG, agentic AI. I'll talk about OpenClaw, and finally some lessons and practices from In Canada AI. So firstly, maybe we can start with the simple question, the RAG, the basic RAG. So RAG, retrieval augmented generation, is the key architecture pattern for granting LMs in some private data. So it includes retrieval part, which you retrieve the snippets from a knowledge base, and augmentation, you after retrieve, you add these snippets into the user prompt, and then based on this provided context, the LM can combine it and leverage it to generate a good answer to the student, to any users. Then we think about, that's the basic RAG. Typically for an enterprise RAG, it has higher requirements. Usually there are 5 phases differs from basic RAG. First is the scalability, because for the enterprise, they usually have millions of documents, not just hundreds. And heterogeneity, because we want to make sure that every source formats can be inputted, and make sure that there's no failure mode. So that's another trick. And compliance. For enterprise RAG, we deal with a lot of personal identifiable information when you handle the privacy, the data residency, etc. And also for the output, usually among cost, latency, and accuracy, there is a trade-off triangle. You cannot keep all of 3 very high. You only pick 2. If you want to prioritize the cost and latency, usually you tolerate a little bit on the lower accuracy. And also the access control. For example, like different user, they have a different document level permission for personalization. So some kind of the access control need to be added on the top of the basic RAG. Okay, and today's production stack, usually we do dense plus sparse retrieval. The dense retrieval meaning that during the retrieve, we combine both the constant similarity, we retrieve some chunks from the database, not only consider the semantic similarity, but also for sparse retrieval, we want to consider keywords. That's the retrieval part. And after we retrieve the most relevant chunks, we also usually use a cross-encoder re-ranking to find the top 10, top K trunkings, and then generation. So some tips here are, first, the trunking is the most underrated lever. When we do usually during the trunking process, the layout aware parser usually beat just the PDF to text trunking mode. And multimodal retrieval is the first class, especially when the data source have a lot of tables, charts, and images. We need to build multimodal retrieval. And the operational layer, so there are a lot of other amorphous work that separates from the just building a demo. So first of all, evaluation. We can use golden data sets or RAGAS. RAGAS is a framework to evaluate the quality of the RAG. But to be noted that the offline evaluation usually is not equals to the online quality. So no matter how much we evaluate on the developer side, we still need to build a full feedback loop to evaluate the entire system and eventually on the user's satisfaction. And secondly, the freshness. So in the enterprise RAG, keeping the data set updated is very important. We should do like incremental updates, deletions, and troubleshooting, and also scale vectors, silently degrade retrieval quality. Third is the observability part. So for example, like the user feedback loop and the retrieval analytics, we need to have some kind of the monitor and to observe the retrieval through all the process. And also the permissions at query time. As an example, some kind of access control that I mentioned, if like a guardrail, when a user asks for something, we may not always answer all the questions, but to some extent, if the question is within the scope of the RAG, then we answer it. So some kind of guardrail or permission control access at every query time is needed. Here is a architecture for an enterprise RAG. In Kendo also built like this. So initially when user initiate a question, it goes through a guardrail, and the system detects whether this is we have the expected input from the system. If it's not expected, then we directly go to the final response. If this is a question that we need to leverage the enterprise RAG, then we first rewrite the query before retrieval, and then consider the chat history. We retrieve it. We retrieve some information through encoder and document injection. and then we do re-ranking, generation, consider all the history storage, user experience storage, and then we output the final answer. Okay, so here you can see the static RAG have some drawbacks. Usually the drawbacks is it's a single step retrieval. So there is no iterative reasoning. And it's pretty limited on the context persistence. So when we need, when there is a multi-step task, it usually hits a wall. So we consider agentic RAG for a better retrieval and enterprise retrieval. So the agentic RAG can unlock what are the benefits. First of all, it can do some kind of planning and reasoning and execute, like a agent can do multiple steps using tools and memories, and it adapts during the execution. So it just not just respond to the initial query, while after thinking, it can use some tools to do some execution, and then to do next step, etc. And usually, if you have a knowledge graph, the static RAG cannot do too much with the knowledge graph, but agentic with agentic workflow, it iteratively retrieve something, and it can go back and to find some relevant information from the knowledge graph, and then do retrieval again and execution. So it dramatically increased the quality of the retrieval. So here are some takeaways. Most RAG problems are retrieval problems, not LLM problems. And re-ranking beats a better embedding model 9 times out of 10. So if you are deploying RAG in 2026 without agentic architecture, basically you are building a 2024 system. So let's go to the part 2. We'll introduce some agentic AI workflow. Compared to the basic RAG, agentic AI have 3 more things. One is the dynamic retrieval, the context fetched in response to reasoning state, not just the initial query. And it usually have the compaction, summarize the chat history, and plan as the first class architecture step, and also have agentic memory as, for example, every tool will have its own memory. Yeah, a simple figure on the agentic loop. First, the agent formulate a plan and then execute the plan. And then we have some level of observation to observe what's going on after the execution. And we give that observation back to the agent, so the agent can adjust the strategy and redo the plan. And then again until the agent finished the job. Okay, and here's the agent architecture. We basically 4 core components for every agent system. There's a planning part, and execution part, refinement, and interface, user interface part. So here we can, it's my label. You can define like AI, the level 1. If you build any position, any system, the level 1 is AI workflow. you use LLM or some AI to output some decision. And the level 2 will be you have a router section in the system. So the system can automatically choose, make some decisions and use different agents to do different tasks. That's the level 2 system. For a level 3, which will be fully autonomous agents, you use LLM as a judge. And the LLM can make decisions, and also the LLM can write a tool and go back and forth, iterative planning, execution until the work is done. That's what I define level 1, 2, and 3. Will be also used it in the later slides. Okay, and so the agent, here are some patterns that work in the production with the agentic workflow. First, you can use like a React single agent. React means it always go to action. It's go to the action, observation, and then backend plan. So learn, act, and observation. Second is like a planner, executor. You can use like a multi-agent with any one agent specialized with some task, and coordinator by a router to a router coordinate these multiple agents. Or you have a swarm agent and sequential chain. So with all of these agents, the protocol layer in 2025 to 2026, there are two popular protocol layers, which is MCP and A2A. So for MCP, you can build like a standards agents, like how this agent work, and you define this in the system. And later on, everyone can use that agent to execute some, to call the agent to do some specialized work. And A2A is an agent-to-agent protocol. Basically, it's a standard in inter-agent communication. So together, MCP plus A2A are becoming the OpenAPI equivalent of the agent stack. So you can build an API, and any other people can use that in their AI systems. And so after that, the evaluation part actually is the hardest part in any AI system. Yeah, here are three very popular framework to evaluate your agentic workflow. The RAGAS is a framework to basically evaluate the RAG part, like to evaluate the retrieval quality. And TrueLens is another framework that evaluate and tracing across the full agent lifecycle. And Deep Eval is another one, especially it's good for MCP2 usage or multimodal inputs. The key takeaway here is evaluation is not an optional infrastructure. It is the primary feedback loop that determines whether your agentic system improves or degrades over time. Okay, and next, let's move on to the part 3. We talk about OpenClaw. On the right of the screen, you can see this is very interesting. After 2026 February, the star history of OpenClaw dramatically increased. So it's a super popular. Even it has. I remember it has more stars than the React agent. So OpenClaw is an open source, autonomous, local first model agnostic agent gateway, and this is a level 3 autonomous agent. The core capability is it can persistently it has persistent memory across sessions, and you feed skills into the system, and it dynamically picks some skills and plugins to execute the work. Also, it has the direct execution tools. It can have access. It access to the browser control. It can read and write the files from your local computer, and also have access for messaging platform. And here is an architecture for OpenClaw. For the 3 layers, the first layer is the messaging adapters. So if you connect OpenClaw with Slack, Discord, email, it can read your message, and that is the interface to receive the user query. And it has brain layer, it's reasoning through LLM, and it can plan and make decisions. And it also has a body layer, have access with tools and conduct actions. And for the memory, it also has memory systems, basically 2 primary memory systems. One is the memory wiki, persistent structured memory across all the sessions, and also has a memory built by the learning from the interactions between all the pattern synthesis. Okay, and here's a 7-stage agentic loop for OpenClaw. Normalize is standard input across channels like WeChat, Slack. It gets the information from all of this messaging platform, and then it has a router system to determine which task that it need to be done. And after that, it can get content, like go to do some search or web search, or check out the memory to gather relevant information. And then it run the LLM reasoning step to plan the work, and then use agent to execute the work. And it also can load all the skills. As a user, you can feed some skills for the system. For example, like if we build like a website, you can upload like a skill for how to build a website, like UI, UX design, rules, structure to fit it. And the agent will leverage that skills to execute. And once the job is done, it also write the memory, like save the state and learnings into the persistent memory. So basically, all the agentic loop go over these 7 stages. And comparing to the enterprise, what are the different features between OpenClaw and enterprise RAG? Here's a simple summary. For the OpenClaw, it's a single user. So the OpenClaw access to your local computer, and you are the only one to input the information to the OpenClaw. And enterprise RAG, it supports multiple user, a lot of different users. It's a multi-tenant system. And for OpenClaw, you need to give it access, like permission, like what files you can the OpenClaw can access. Like you give it your messaging access, file access, or your code base access, then it can read and to work. And for enterprise, it's a role-based. So you define this agent, every agent's scope, and what can do, what cannot do. It's very clearly defined. So similarly, the enterprise RAG has vetted tools. Every tool is clearly defined to handle some level of the task, the very specific defined in the system. But the OpenClaw is unvetted skills. You don't need to do much, and you even also don't know what are the things that OpenClaw will utilize to execute the work. And it's local trust boundary. But for the enterprise, it's like a cloud trust boundary. So based on these three features, like local for OpenClaw, it uses local privileged access, and it's also untrusted plugin, and also there's no controlled permissions in during the agent execution process. So based on these three features, security surface enterprise usually cannot accept OpenClaw. That's why in our company, we also haven't implement this for the enterprise level. Okay, finally, it's our company's agentic workflow. In Candle, we utilize agentic workflow as an example. We have a 24/7 teaching assistant. We call it ChatTA. For the ChatTA, we have built the short-term memory to have user level for every user's chat history. We summarize it, build it into the database, and yeah, that's our short-term working memory. And also for some user features and persistent context, we also build a long-term knowledge database for that. So the motivation and the outcome for building that is for every user, we can provide personalized tutoring for different students. And we also adopt multi-agent orchestration. As an example, we have a lesson planner agent. The lesson planner can read the in the lesson planner agent, we have several in this section, we have several different specialized agents. So we have the curriculum design agent to retrieve the curriculum relevant information. And we have research agent to do some research on the top of it. And then we have content writer agent. And finally, we also have a review agent to make sure that every content we write is correct. And in this this multi-agent orchestration is powered. We adopted long graph to build this, and there's a human in the loop at every step. Okay, yeah, and for the evaluation part, we also have multiple evaluation strategies like golden data set. Basically, it's quantitative analysis and qualitative analysis from user surveys, etc. Yeah, and the next step will also the vision of Incandle is also to build like autonomous agentic workflow that every teaching and learning system not only perform but also can self-manage and self-improve. That's the future goal for the Incandle AI. Thank you very much. Thank you, everyone. If you have any, I'm happy to answer any questions if you have.
Yeah, thank you, Doctor. And I see one of our questions from the audience is, what is the most important safety risk from OpenClaw to you?
Sure. Yeah, actually, I have a slide based on the time limitation. I didn't. Can you see my screen now?
Yeah, yeah, yeah.
Yeah, for the open call, there are basically four risks for the enterprise to adopt. First of all, it's the security part. Um, it usually require a high level privilege, like for every need to have access on the local files and code base. That is the primary risk for enterprise because we are worried about that whether this level of the access will leak company's information. So that's number one. And second is the OpenClaw is very autonomous. So basically, from the agent to talk to agent, if one agent has some hallucination, there's no control of us to monitor every steps, every input and output between the agents. So there is a trust issue. And third is unpredictable execution. We're based on human in the loop, so it's still a bit not trustworthy to rely solely on the autonomous loops data. And also for the it's a budget consideration. It's if we're unsure about every input and output within one agent, well, we cannot do a very good budget control, like tokens, how much tokens that we use. So that is a big business decision that we cannot trust OpenClaw at this stage. And also the data privacy is another risk. So if OpenClaw has multiple access to the files, there is a risk that it will use one user's files information to answer another user's question. So that kind of information leakage is can be a failure mode, and also it's a risk for enterprise level to consider. I hope that answered the questions.
Yeah, great. Thank you again for that amazing talk. So let's now move on to the second talk, which will be given by Dr. Yu Gu. Hi, Doctor. Are you with us?
Bruce, can you hear me?
Yeah, I can hear you.
Okay, let me share my screen first. Sorry, it's the first time using StreamYard.
Yeah, it's okay. Take your time.
Am I sharing my slide?
Yeah, I can see your screen now.
Okay, cool. So we can start. Hello, everyone. I'm super honored to be invited to give a talk regarding my recent reflections on self-improvement agents. So my talk today will mostly be some high-level ideas and principles. So I won't touch any concrete architectures or concrete technical details. So hopefully, the talk is not going to be too heavy. um, yeah, so basically, self-improvement agents is really becoming a thing recently. I think everyone probably has already noticed that. So, for example, like even OpenClaw, right? OpenClaw also kind of like positioning itself as something that can continuously improve based on interaction with users. And also more recently, Hermes agent is basically directly brand itself as the agent that grows with you. And also, like some other open source projects, and also like for the Claw Hub, which is basically the kind of like a centralized platform for open Claw skills. You can see on its leaderboard like the top 4 most downloaded skills, like 2 out of them are about self-improving. So it's really kind of like hype and it's kind of like buzzword recently. But why we want self-improving? That's the first thing that I wanna touch. So what's the motivation here? I think motivation is very simple. So let's first think about some background here. So learning is still mostly a passive setting in the in the context of LLMs today. So what does it mean? It basically means to train your large language models, it still mostly rely on human experts to control the whole flow of model training, including data curation. So it's purely passive. However, people know that data quickly become a bottleneck for all these kind of like big techs or frontier labs, right? Majority of training LLMs is about like creating new data or creating the environment to collect data. However, a fact is that though we have mostly exploited the existing documented data, but still these undocumented data, like interactions, are still largely underexploited. For example, a lot of like human knowledge are not really documented in the maybe in the web or somewhere else. It's many about like through, for example, a lot of like uh, knowledge about a company's business logic that happens within like the maybe the offline discussions happens within the interaction between the user or the employees and the the maybe their SaaS softwares. So all these kind of interactions are not captured at all for training the model, which is like a big loss. So imagine more boldly, if we want to get the data to saturate the 10T or even 100T model in the future, we definitely want to have a new paradigm to unlock like more learning signals, which is basically just going to be the interactions. And this is tightly related to the term self-improving. So imagine if your agent can actually learn during deployment, can learn actually from the interactions with like the user, then those it's gonna unlock like 10 times or 1,000 times of the training data we can get today just through the documented data. Yeah, so that's some basic motivation regarding self-improving, and I think this is why it kind of like becomes popular recently, because the fundamental reason is still we're kind of like saturating the passive setting at this point. Yeah, so I think the core topic today is about like I really want to talk about several principles that make your agent truly self-improve. So I think first we can decompose self-improving to two terms. One is proactiveness, and the second is learning. So for proactiveness, it's more about like so what and when your agent needs to decide what to learn and when to learn by itself. But learning is more about like how it concretely improves, how the learning progress actually happens. So today I will be focusing more on the how part or the learning part, and I will only be briefly touching the proactiveness part. So regarding learning, I think it's one very interesting view I kind of like regarding learning from the cognitive science or psychology is learning can be viewed as the evolution of memory. So basically it means that like in maybe cognitive neuroscience, learning is typically understood as a way to kind of like update memory or to change like how the synapse connected. And memory is basically how uh, the updated synapse connection can guide the behavior of the agent. So they are kind of like two sides of the same coin. And so more concretely, if we take the view of learning as evolution of memory, there can be more there can be three aspects, three dimensions, inseparable dimensions. Well, the first dimension is how to represent the memory. The second dimension is how to update memory. And third dimension is how to use memory, right? They are kind of like inseparable, particularly the first dimension and the second dimension, like how do you present and how do you update. They can be tightly coupled. So I think this is going to be the most important slide for my talk today. So it's going to be talking about the first principles or the qualities of the data we want for learning. So first, for the representation part, I think the core of representation is that we really want to form some abstraction and structure of the knowledge instead of just kind of like memorizing everything or taking notes of everything. We need to form a more abstract representation of the memory. We need to kind of like find the common patterns from these concrete cases or concrete interactions. A second part is about update, right? So after we have the memory representation, we need to have a way to reliably update the memory so we can reliably integrate new information from different sources, including like we need to resolve conflicts from different sources of information, right? That's kind of like also the core of human learning. We need to integrate things into a self-contained system. And the third part is the execution, right? After we have the memory, this is about the usage of memory. After we have the memory, how can we use the memory to guide execution? So I think the key is that we really need to form a closed loop validation for execution guided by memory instead of just using the memory as part of like the prompts, which is very shallow. So let's first talk about the representation and update part a bit. So one thing I want to emphasize about memory representation here is that so memory is kind of like unified term. It's not a shallow term or it's not a narrow term that just mean the external memory of LLMs like the markdown files, like vector databases people are mainly talking about these days. It also can be referred to like model weights. If you think about that, like model weights is also itself a form of long-term memory, right? Because that's how our like the deep learning models or machine learning models like capture the knowledge in like the distributed representation. So a core aspect of memory representation, as we discussed before, is we need to form abstraction. We need to kind of like form new conceptualization instead of like just noting things down, like just memorizing things. So I think it's actually quite interesting. Like the term concept is related to several other frequently used terms, like abstraction we have been talking about, right? We need to kind of like mine the concept from the interactions. We need to form the abstraction, which is also related to reuse. So with the same abstraction, you can use it to point to different cases. You can reuse abstraction. And also, if you are familiar with the compression algorithm in computer science, you might see that reuse is actually a core assumption regarding compression, right? Because for example, like some classic compression algorithm like GZIP, it mainly based on finding the common patterns, common strings, and then you can use that to compress your representation. So, and this is also tightly related to compressionist intelligence, which further leads to generalization. So basically, the core concept here is that we need to have a way to better abstract the knowledge into a more abstract representation of the memory. However, to reliably form a concept, we need to have some good structure. So here's a very, very intuitive example. It may not be directly related to agent per se, but mostly as an intuitive example for people to understand the high-level intuition here. Say like this is actually an example I quite like. So say like a baby learns to form the concept of a cat and a dog, but the first time the baby saw a cat, it might be a brown cat, and the first time the baby saw a dog, it might be a white dog. Then it might form some shallow rule like cat should be something brown and dog should be something white, right? If it just memorize some knowledge as this, you can imagine it's similar to how today's agent write down the knowledge into a markdown file. It's just write down two statements like this, and then if the baby saw a white cat, it introduced some conflicts, and the baby could be confusing regarding how to update knowledge, right? It's very hard. You cannot trace down to the provenance. You don't know how to update your knowledge more properly. But by contrast, if we have a good structure of the memory representation, like you do kind of like have tree representation of the cat and dog taxonomy, including features among like shape, ears, you can actually easily evolve your structure representation to better classify a cat in the future. So note that this is just a very high level idea, just to give you an intuition. So the topic itself may not be super relevant and important here. And similarly, if we look at a more concrete example, like say like many of today's self-improvement agents is about really learning user preference. So if we look at like how the agent learn user preference from user interactions, so there are several turns. So in the first two turns, the user orders either iced latte or orders cold brew, and then in the third turn, the user orders hot latte. Uh, Without a structure. So after the agent saw the first two turns, it might write down something like the user prefers cold drinks based on the first two turns. But then if the agent saw the third turn, it also introduce like conflict and does not have a good way to incorporate it into the memory representation because of the lack of a good structure. But if we have a structure, for example, like we kind of like structure the representation based on temperature and type, it might give you a better opportunity to capture things more precisely. Yeah, but still, this is a very naive example and very preliminary example. In the real world, if you really want your agent to capture something much more complex, for example, like a procedure knowledge of about like how do you doing some concrete operations in like a domain specific software or something like that, the representation should be much more structured and more complex. So if we revisit existing solutions based on our view of like structure and update, so for the popular scales system, basically markdown files, it has certain level of abstraction and compression, right? Because it basically asks the agent to crystallize a trace or something into a short natural language description. However, there's almost no structure because the markdown files is mostly free form text. So it does not have the right structure for us to reliably update things. And as a result, update is done mainly through rewriting. You can imagine the writing is also quite like unconstrained. As a result, it's really hard for us to guarantee we can do the reliable update or reliable integration of different sources, including handle conflicting information as we saw in the previous slide. For vector databases, it's even worse. It's almost no abstraction compression. You're basically just appending new items to the vector database. The update is done mainly through appending, and there's no abstraction, no good structure. But for the model weights, I think model weights is actually a good way to achieve both good representation and structure in terms of geometric structure. And also it can achieve reliable update over large training set while mature techniques like gradient descent. However, the thing is that we know like for this kind of like learning, it suffers from catastrophic forgetting in continued learning, right? And personally, I think it's really hard to achieve true continued learning with model weights update without access to a large replay buffer or something like that. So as a result, I think today is actually a good opportunity for us to maybe think a bit more about how do you achieve like the good representation and structure, which can support reliable update in the context of non-parametric learning. Luckily, I think we can actually learn a lot of lessons from symbolic AI. So for example, this is probably a paper from like 20 years ago. It's actually addressed exactly the same scenario we just discussed, like how we can handle like the conflict information in modeling user preference. So basically, so in symbolic AI, people have already studied a lot of like techniques. Like we can add priority to override the knowledge. We need to kind of like derive provenance and confidence for every statement, and also we need to do some multi-context management. So multi-context management basically means some statement might be true given different conditions. So yeah, so basically there's some high-level ideas that we can leverage from symbolic AI. I think it's actually like a good opportunity for some aspects of symbolic AI to come back, maybe except for their focus on the concrete form of knowledge representation. Okay, so that's many about the update and representation. And the final piece regarding learning is execution with memory, right? Remember, we have 3 dimensions regarding learning as an evolution of memory. So I think one missing piece in most existing self-improving agents is that, as we also mentioned at the beginning, that memory is simply used as part of the prompts. You just inject the memory from the markdown files into the prompts, and then everything is offloaded to the LM itself. You just expect the LM can understand your memory properly and can do the execution strictly following the memory. However, there can be like two fundamental issues. Right. The first thing is, right, there's no guarantee of execution as we just mentioned, because agent or the LLM may ignore or misuse the memory because it's just a part of the prompt. You don't know what behavior of the LLM will be. It's totally unpredictable. And the second part is that I think personally, I think this is actually a more serious problem, more systematic issue. So because we are not indeed executing the memory, we are not indeed exerting the knowledge. So there's no direct feedback for learning. As a result, failures are not grounded, which also comes back to the aspect of learning, because we do not have like grounded signals regarding the failure. It also makes it harder to diagnose where went wrong, and as a result, it makes fix the memory or makes continued learning more challenging. So, for example, if the memory is kind of like represented as an executable script, then if we directly execute the script itself, and it might fail at a certain step, this kind of a failure will directly inform us where the memory went wrong, and we can directly fix the exact step in the script. However, if the memory is just used as a prompt, then it's really hard for us to tell which part it went wrong. Is it just about the memory itself, or it's maybe the LM is not good enough? Right. So the key point here is that we really need to put the memory inside the execution loop. And this is kind of like a thing I have been talking about for a while. Like, I think the key here is that learning and inference should not be separated. That is also how human beings learn new things, right? We are not like statistic models, which have like a modeling or learning stage and an inference stage. We kind of like interleave both learning and inference. We learn new things when we do inference, right? So that's kind of like a core idea here. Okay, so last but not least, remember regarding self-improving, there's also the proactiveness part. So for this part, I only have like one recommended reading, so which is a recent paper from Meta. The title is "Why AI Systems Don't Learn and What to Do About It." So basically, the idea is very simple. So, it kind of like builds on top of some findings from cognitive science, where humans learning takes like two forms. One is called System A, which is basically learning from observations. It's just like how we learn by reading a book, or by learning by attending like a lectures or something like that. But the second form is called System B, which is basically learning from actions from trial and errors, which is more similar to the reinforcement learning setting, right? So it's kind of like in the machine learning term is just like supervised learning setting and reinforcement learning setting. And on top of that, so one interesting thing about humans learning is that human do not only takes the fixed form. Instead, human can flexibly change the pattern of learning. And this is basically what the system M does. It's kind of like a meta control layer that decides when to do system A learning and when to do system B learning. And this is indeed exactly where the proactiveness of human learning comes from. And we can actually get some inspiration from there. We can also do the same thing for agent, right? If we have like a meta control layer, and then the agent can just use a meta control layer to decide when to invoke system A learning, when to invoke system B learning, and what data to use for system A learning, etc. So that's kind of like a very interesting work, and I definitely recommend people checking that out. Yeah. So to quickly summarize what we have been discussing today, so first, there's a centralized view regarding learning, which is evolution of memory, and this is kind of like the fundamental of everything following up. And also, we talked about several key principles regarding a real self-improving system. First is going to be the structure representation, structure abstraction of the memory, and then we need to have a more reliable mechanism for updating the memory. And then we need to have the closed loop execution. So we really need a memory to be part of the execution, not just part of the prompt. And also we need a proactiveness and meta control layer. So the agent can actually learn in a more proactive, more active way, not just a passive setting, so as to achieve the so-called like self-improving, not passive improving. However, like most current systems, they lack a good structure. For example, they just use markdown files to represent the skills, and they just evolve the markdown files, which does not have reliable update, right? They just rewrite the markdown file. Sometimes it may be just regenerate an entirely new markdown file that also conflicts or incompatible with the previous version. And also, most of the markdown files or markdown skills, they're just injected as part of the prompt. So there's no closed loop for execution. And also, as a result, AI accumulate data but may not truly learn. Okay, so yeah, that's all for my sharing today, and I'm happy to take any questions.
Yeah, thank you, Doctor. I think we have one question from the audience here is, what are the most common mistakes in evaluating self-improving agents?
Mm. Yeah, I think that's a good question. So basically, I think at the high level, most important missing piece is that people today, when talking about like evaluation in the context of LLMs, we are generally too like focusing on the empirical results. However, we on top of empirical results, we also want to have more like principled understanding. We do have some more like qualitative understanding instead of just quantitative results. For example, like in my talk today, we have been talking about three different desiderata regarding self-improving, right? But in today's evaluation system for self-improving agents, we don't actually try to understand the self-improving agents from these dimensions, which I think is kind of like critical missing piece in really evaluating self-improving. So in the future, we definitely want to have a way to better evaluating self-improvement agents in a more principled way, like across these dimensions. But to be honest, I don't have a very concrete idea regarding how to implement the evaluation at this point. But I think this should be enough as a kind of like high-level guidance for the future evaluation.
Okay, thank you. Thank you again for sharing. That was inspiring. So
Yeah, thank you.
now let's move on to the third talk, which will be given by Dr. Weiming Lu. Hello, Doctor. Are you with us?
Yes, can you hear me?
Yeah, I can hear you.
Let me see how to share slides and one second. It's uploading.
Okay.
Sorry, I didn't realize.
Yeah, I think you may just
It
need
didn't
to.
recognize. It didn't recognize my app. I use WPS, so I need
You
to
can just
upload.
click the
Yeah.
icon in the bottom to share the
Yeah.
screen.
Oh, I see. Yeah, it's still processing. Sorry for that.
Yeah, it's okay.
Okay. Okay. For some reason, it didn't recognize.
Yeah, now we can see your screen.
Oh, you can see my screen? Okay, good, great.
Yeah, you can start whenever you are ready.
Okay. Can you see the screen?
Yeah.
These slides? Okay. Oh, thank you very much for inviting me to give this talk. I would like to give a high-level overview about the cognitive agent, and I will focus on the two pillars of the cognitive agent, agent native memory and the continuous learning. And Dr. Gao and Gu both talked about these topics from different angles. Okay, so that's the agenda for today. And first, brief define the cognitive agent paradigm, and we focus on the core pillars. And then I will discuss the agent native memory architectures and also the continuous learning with focus on the use reinforcement learning techniques. And finally, bring things together. I will talk about the harness engineering and how to develop a cognitive agent. First, the concept of AI was closely tied to agent from the early formation of the discipline of AI. For example, the Dartmouth conference. So the evolution of AI basically is the evolution of agents. In particular, in the past, since 2022, with the emergence of the ChatGPT. However, the early agent is more like a stateless chatbot, like ChatGPT, and only one round of conversation, so with no memory and context of past conversations. And now the ChatGPT or other chatbot evolved into a stateful assistant. They can remember the conversational history about the current session. However, all data won't be used when you start a new session. And so the ultimate goal for the agent is the cognitive agent, which possess persistent memory and also continuous learning capability. So it will enable long-term goal-oriented collaboration. And there are three in the framework for the agent consists of three parts. Basically, is a perception. So the agent will observe the raw environment state and the process.
Yeah, sorry,
to
doctor.
produce.
We can only see the cover of your slides.
Oh, really? Okay. Let me see.
Yeah, now it's good.
Oh,
Now it's the
here.
agenda.
Okay. I see. Yeah, I just talked about the three-part framework for the agent. The perception, the sensor, the brain, which is a reasoner to maintain a historical memory, and generate latent thoughts and plans and make decision to produce the actions based on the observation, and also the action which execute the action policy. For the perception module, so the core role is act as the agent sensor. So it perceives the raw environment state and convert the state into a structured, interpretable observation for the reasoning module. The brain so is the central controller for the agent, and so there consist of three major functionalities. First is memory management, and so maintain a mutable internal state that dynamically represents the agent's accumulated knowledge and the interaction history. And also the cognitive planning, so generating structured latent reasoning, including the thoughts, plans, and also some kind of justifications to guide future actions. And also the action policy, which to synthesizing the information to decide on a specific optimal action to execute within the current environment context. And for the so the three components form a feedback loop. So you start from the agent to execute action, and so to interact with the environment, so kickstart the interaction cycle with the external system. And the environment provide the feedback and the react, and so the for the agent to get the information about the state of the environment, and the brain will update the memory based on the feedback from the environment and also the memory history. So this closed loop mechanism is essential core for the agent learning and adaptation. So so you will iteratively refine the agent behavior based on the real-time environment feedback. So to define the cognitive agent, the two pillars for the for the cognitive agents are the agent native memory and the capacities for the continuous learning. So the agent native memory so the definition is to persistently retain and recall information across interactions and time. So it's not just the context window, but a structured, evolving knowledge base. And for the continuous learning, so it's the ability for the agent to learn on the fly through the interaction feedback from the environment. So together, this pillar enable agent to adapt, personalize, and exhibit a form of autonomy that goes beyond simple task execution. Let's first talk about the agent native memory architecture. So why we should consider this option? Because right now, the current generative AI application as observe the auto context of problems. Mainly there, for example, so semantic drift. So the reasoning space and also the retrieval space are separated semantically. So that will need to the irrelevant and contradictory results. And the lost context, no matter it's a long session or cross-session conversation, and it's usually we will see there's some kind of forget what the conversation, the content of the conversation before, and the inefficiency, and because of the variety of different kinds of memory type And so the designer of the agent will usually adopt different kinds of system, for example, different database or the data management system to accommodate those kind of data and memory. However, those kind of broken system or the fragmented approach usually generate introduce significant latency and computational overhead. And so this make the user experience less appealing. So how to address this problem? And we define the agent-native memory. So which basically is the agent not just reasons, but also curates structures and retrieve knowledge as the first class tools, and making the memory a core part of the cognition. And there's three major characteristics about the agent-native memory. First, it's deeply integrated into the process. And then, so the agent would actively curate the data and memory so for example, it's organized structure, prompts, and evolves its knowledge base for relevance and efficiency. And the third part is a context awareness. So the memory system dynamically understands the agent's current goal and plans. So this approach would fundamentally treat memory as a core cognitive function of the agent, not just afterthought or eternal add-on. So there are 5 major kinds of agent-native memory system. And the first is sensory memory, which captures the raw sensory input from the environment. And the working memory is a temporary host and manipulates information needed for current session. And episodic memory, which basically stores personal information and specific event sequences with a temporal context. And the semantic memory is something that retains general word knowledge, facts, and the concepts independent of specific sessions. And the procedural memory, so is something to incorporate learned skills, habits, and step-by-step procedures for performing complex tasks. And at Actonus, we define what we call cognitive memory, and which is the memory solution for the cognitive agent. And we're moving from the layered memory to a full memory operating system designed for cognitive assets. It's a paradigm shift. So from a single storage to an end-to-end lifecycle management system for all the agents' knowledge and experience. The core idea is to treat the memory not just as a data store, but as a living, evolving ecosystem that needs active management to remain healthy and useful. And the scope for the cognitive MEM is they manage not just what is remembered, but how it is encoded, retrieved, consolidated, and eventually forgotten. So the cognitive MEM is an enterprise level class agent-native memory solution. They provide the hierarchical layered solution to address the different kind of memory type. And so we offer this is a integrated solution by combining the solution for short-term memory, long-term memory, agent artifacts, knowledge graph, and the reasoning traces. So this unified approach breaks down the storage barrier. Yeah. So the cognitive MEM offer the life cycle of management for the memory system for the agent. So the starting from the beginning, they ingest the capture inputs, outputs, action logs, and the reasoning traces, and they encode those memory, offer multi-modality capability, and they retrieve the information with optimized results, and also compaction to do the merging, the duplication, conflict resolution, etc. And they evolve the memory, and for example, they provide version tracking, dynamic updates, knowledge graph, etc. And forget whenever they're need, based on the freshness and the relevance, they just prompt the memory from the memory, the knowledge base. Another example for this type of information is for the consumer use is Carpathes LLM Wiki. So they propose a compilation over retrieval, this kind of approach, which instead of searching the raw data, and the LLM acts as a compiler that ingests raw materials and construct a structured, interconnected, self-growing encyclopedia. And however, this kind of solution is for basically for the personal use, and so it's different from what we propose, the enterprise-grade memory solution. However, so the idea basically is the same. And next, let's talk about the continuous learning and the reinforcement learning. And the framework for the reinforcement learning is as follows. And so basically, for the reinforcement learning, an agent learns to make an optimal decision based on the actions within the environment, and also the information they received as a feedback in the form of rewards and penalties. And one of the core concept is the reward model. The reward model can be defined, from the first principle, or in the large language model setting. And so usually we use human feedback to train the reward model. And the reinforcement learning plays a significant role in the LLM training, and in particular in the post-training and test time computing. In the post-training, they use reinforcement learning with human feedback, so it made to make the model richer and more flexible. And for the agentic tuning, so the recent reinforcement learning with verified reward provide effective techniques for the reinforcement learning in the large language model training. Of course, it can also be used in the post-training phase, and so in the agentic setting, and it provide a tool to enhance models' learning ability, in particular to implant the model with more agentic behaviors. So for the reinforcement learning, so we need to train the reward model from the prompt sampled from the data set, and is offered a response level reward learned from the human preferences. For the reinforcement learning with verifiable rewards, so they apply the same algorithm to LLMs However, the answer is checked directly without training a reward model. And so that make the computation more scalable, and in particular is very useful in the inference time compute. And so reinforcement learning is a very effective tool for the continuous learning for the agent. And for example, people use reinforcement learning for agents, in the case of OpenClaw. And so there are some kind of OpenClaw reinforcement learning approach. It provides a learning framework designed to recover next state signals and turning the feedback loops into continuous learning cycles. And also scale RL. So they also use reinforcement learning to learn reusable skills. And so that's also very important for the self-improving agent to produce. Yeah, so that's the brief introduction about the continuous learning. And now let's turn to the right now very popular harness engineering. So why this is important? Because for the cognitive agents, and so both memory and continuous learning capabilities are very important components for the cognitive agent to adapt and to self-improve. So the memory and the continuous learning are tied very closely during this process. So for the cognitive agent, by integrating the agent native memory and also continuous learning capability, we can offer very unified framework by achieving that. And for example, they interact and store the memory and the knowledge, and then they learn and replay. When they learn a new task, they use the replay for avoiding the catastrophic forgetting, and also they consolidate the memories, and also with those information update their skills and to adapt the new situation. So for the case of harness engineering, why this is very important, because as agents become more capable, the role of human developer evolves from code writing to ecosystem building. So the developer responsibility would focus more on design environment, specify intent, and build feedback loops that allow agents to do reliable work. So that's very different from traditional development, which primarily focus on manually implementing those kind of logic and algorithms. Also, the harness engineering evolved very rapidly, and we can see from Anthropic's experience. And so last year, they published a blog called "Building Effective Agents," and they recognized the importance of the verification loop. For example, they defined 6 patterns. One of the patterns is evaluation and optimization. So soon after, the another blog we see is how we build our multi-agent research system, and so by using multiple agents, sub-agent to deal with different tasks, and so to achieve a common goal. And later they found they experienced some catastrophic forgetting, in particular for the long-running agent. And so that's the initial idea for the harness engineering. So they published another block is called Effect Harness for Long-Running Agents. And so they define two major agents, initializer and the coding robot, and to handle this kind of non-running agent problem. And more recently, they realized during all this process, they need to separate the rule for the generation and the verification. And so the importance of cross-verification in this kind of verification loop is very important. So that's another blog post from Anthropic. And so of course this hard engineering is still evolving. And so no matter what, and so we this is kind of very important for the cognitive agent development. And so the harness engineering basically used as a glue to tie different components together. And during the for the development of cognitive agent, there are four pillars to effectively doing that. And for example, vibes used to define the culture, style, ethic, boundary, etc. To align the agent behavior. And also the specifications is record the living dynamic document, provide the documentation. So the agent can read, understand, and reference during this kind of operation. The skills basically provide different kind of tools necessary for achieving the desired goal. And finally, the agent provide execution platform and to leverage the norms, the vibes, the specs, and the skills. So this type of process for the design, develop the agent, there is some mechanism can follow, which is called Ralph-Vaughan loop. So it's an iterative development cycle designed for seamless human-agent collaboration. So that recently there's a leakage for the source code for the cloud code, and the people analyze this code base, and so they learned something. Some information about the architecture for the cloud code, and so that's something is something people very effective in coding and other tasks using this type of framework. So that's all for what I would like to share, and so our goal is toward a cognitive agent by sharpen the agent native memory and improve the online learning capability, and leverage harness engineering to design the ultimate cognitive agent. Thank you very much.
Yeah, thank you, Doctor. We have one question from the audience here. Is that what makes agent native memory different from traditional memory systems?
Yeah, thanks. A very good question. Yeah, there are multiple dimensions we can compare these two. And so, for example, the agent native memory is a first-class citizen deeply woven into the agent's internal reasoning. That's one aspect. For another aspect, for the traditional memory is kind of more or less like passively storing data, and for the agent native memory, will actively curate, organize, and prompts knowledge for the maximum relevance, and also for the agent native memory is maintain a dynamic context awareness by actively understanding the agent's specific memory planning and access goals. And also for the agent native memory, the system utilize a full the full component which mirror the human cognition, including, for example, sensory, working, episodic, semantic, and procedural memory. And finally, with the agent memory, native memory approach, it's kind of unified approach, which breaks down data silos, enabling cross-type reasoning and automatic discovery of emergent knowledge. Yeah, so definitely there's a lot of advantage for the agent native memory approach. Yeah.
Yeah, thank you. Thank you again for your amazing talk. Now, let's move on to the panelist discussion part, which will be led by Dr. Yuxi Li. Hi, Dr. Li. Are you with us?
Hello.
Hi.
Hi, yeah, that's very exciting talk. I think, yeah, for question is, I think you touched this somehow here and there, but maybe you want to give a brief summary. So what do you think the challenges and opportunities for the language model agents? Yeah, maybe who wants to do first? Maybe lady first, Wujun?
Yeah. Yeah, the opportunities definitely is big, it's huge. Basically, you can know everything. We can add a interface layer, which we use natural language to control and do a lot of automate a lot of workflow through large language model layer. I think that's the most exciting part, making automate the workflow and improve the efficiency. Challenge also a lot. I think one biggest challenge is yeah, so far it's still it's still not safe and trustworthy to solely rely on the agent to do the things. So you need to be have some quality control, and I think humans still play an important role in that, like human in the loop and human in the final review. And so I think it's still necessary for the human to participate in the decision-making process.
Okay, Yu?
Oh yeah. Yeah, I think the biggest opportunity for the next step of agents, or particularly agents based on LLM, is definitely what I've been talking about. Like also people have been sharing today. It's kind of like how do you better do the continued learning, right? Because the assumption is that a lot of the knowledge, a lot of the interaction happens in deployment, and currently this is not leveraged at all. Once the model is trained, it's frozen, no update, right? This is a big loss opportunity. And another thing I want to bring up is that, so Dr. Yushi, you may agree or may not agree with this, that I do think one interesting opportunity unlocked by large language models is its potential in manipulating symbols. So it's kind of like an all-around symbol manipulator. As a result, this unlocks the possibility of doing non-parametric learning, or kind of like memory-based learning. The memory can be parameters or non-parameters, right? But before LLM, it's really not possible to do the non-parametric learning at all. So that's just also why a lot of like symbolic AI people, they are kind of actually excited about LLMs, because now they can automate the natural implementation or information extraction with LLMs to automate. And also LLM itself is a good kind of like model that can understand all different kinds of symbols. So I think that's actually an opportunity there. But to actually make it work in a more principled way, there are definitely several dimensions of challenges we need to conquer, as I discussed today. Like, how do you better represent the memory? How do you better guarantee the reliable update of the memory? And how do you better incorporate the memory into the execution loop, something like that? Yeah.
Yeah, maybe it's just one comment. I think your talk, when I hear your talk, I think is basically reinforcement learning. Anyway.
Yeah, right. The high level
I think
idea,
you are using some terms. You don't mention reinforcement learning, but I think basically you are doing reinforcement learning. But anyway.
Yeah, I agree. Actually, I agree.
Yeah. Wimi?
Yeah, I basically agree with both Dr. Gao and Dr. Gu. One thing I would add, actually, recently I read an article, basically a Harvard professor, physics professor, advised AI agent to write PhD thesis in 2 weeks. Usually it takes about 1 year for a human PhD student to do that. And that's very impressive. Of course, there are some other limitations need to conquer. However, and so that's something really not under. Overlook the potential of the AI agents. And so basically the AI agent address the scarcity issue, the scarcity of the human time and the human attention. So a lot of opportunities, and so basically almost in every areas. Yeah.
Okay, yeah, that's great. Yeah, I believe there will be lots of discussion or even debate. So yeah, maybe we can do it offline. Yeah, another question I want to ask is, I think you have lots of experience doing startup, doing research. So, what kinds of suggestions do you want to give to researchers, entrepreneurs, and VCs about agent or even AI? Maybe from Weiming first. Let's do yours.
Okay. Yeah, I will address this issue with the entrepreneur. Yeah, so AI is evolving very fast. And so definitely for you, if you want to start up, you don't want to build another large language model. And so it would be too late and too expensive, and also not very effective, because the large language model right now is good enough for the agent application, no matter it's a closed source model or open source model. Another issue I would like to emphasize is we should focus on more the fundamental issue, those relatively stable and with certainty. So the more because usually when you do something application, for example, and this is the LLM companies, and maybe next morning we wake up and they announce something, some new solution which make your effort useless, right? And so we need to focus something narrow. Instead of to address some kind of general issues, to do something good, and so to build your barrier, and so that's something is what we should do. And for example, we like Dr. Gao built the vertical application, like the AI in the education, and also we are building the cognitive memory system for the enterprise agent application, and those something even the language model changes, and so those solutions definitely will stay and will apply to the new generation of models.
Yeah, I can add a comment on Dr. Wu's statement. Because I built actually start the very basic idea of research, like how to leverage AI to better support engineering education. I initially start with natural language processing with BERT models, and then after ChatGPT came out, I pivoted my research to generative AI and build RAG system, agent system, and finally applied it to vertical applications and supported education sectors. I think my maybe one advice that I can think is, I think all of the groups maybe should stay grounded in real problems, not just model novelty. Academic and real startup, after I did both, I feel it's a big difference. For researchers, we spend a lot of more time on benchmarking, model novelty, some evaluation part. But as entrepreneurs, I think the most important thing is not build an agent looking for a problem, but to start with a user pain point, understand the market, understand where human time is wasted, and then ask whether a large language model or agentic system truly improves that workflow. And then we search for solutions. So that's my learning. Focus less on intelligence in isolation, but more on intelligence inside real systems.
I think both you have talking about some really great advices. So for me, well, it's probably not an advice. It's many. So yeah, I'm like co-founding a startup like for like 1 year, but my experience still many as a researcher. So mostly my personal feelings as a researcher. So I feel it's always important to aim for the essential things. More concretely, I think this is kind of a high level guiding point. It's kind of my life philosophy, just aiming for the essential things. For example, like as a researcher, if you want to do like fundamental research, the only evaluation system is that you need to form your own philosophy. You need to have a self-contained system, right? That can only be told by yourself. But whether this self-contained is actually an objective thing, right? I think that's a metric for if you want to do fundamental research. On the other hand, if you want to do applied research, I think the key is always about you really need to make your research able to be applied, to be deployable. So the only metric there should be, yeah, if you do apply research, then you really need to think about how to convert your research into real commercial values, right? So that's how I think about things. I think we need to always pursue like the essential things not just the surface things. So yeah, I guess maybe that's not a concrete actionable advice. Mostly some general feelings. Yeah.
Yeah, that's great. Yeah, maybe let me ask one more question. Yeah, and it's not quite a question. So, if you just want to say one sentence, so what do we want to say? Maybe Wei Ming first. Just one sentence.
Okay. There's a lot of possibilities for AI agent, but also there's a lot of issue need to be resolved.
Okay, great. You?
Yeah, that's a very interesting question. So one sentence, maybe, yeah. Yeah, one possibility is that I just said like aiming for the essential things. And the second thing is that yeah, maybe you should invest neocognition.
Okay.
Yeah. Okay, yeah, that's it.
Okay, good. Yeah. Rujun, yeah.
Yeah, I think my one sentence conclusion for both my talk and my view is in near term, the most successful agent will not be fully autonomous replacements. They will be highly scoped, true using, and human supervised collaborators. That's my view. Thank you.
Yeah, that's great. I think this is basically finished my questions. So, Bruce, do you have more questions, or do you want to close? Or
Yes, I think we have some questions from the audience.
yeah.
Question one is, how do you see the role of memory involving in agent systems?
So this to all the speakers, or just to Wei Min or somebody.
Yeah, too. I think that's for all of you.
I think memory is the key for creating personalization and persona. Different. That's the key. And also it's also the mode for any company or software, because all the memory we build from user interaction or some kind of user's data. That is I would say the mode to differentiate your product with others. So it's very important.
Okay, thank you. I think we have the last question here is, in your experience, what makes agent systems actually reliable, like rather than just impressive in demos?
Yeah, I think I can also answer that. So in my enterprise rag, I actually mentioned that the key is the reliability, and the reliability needs a very good evaluation. So that those evaluation, for example, like rag level evaluation, and also the system level evaluation, and also end-to-end evaluation, which basically including the developer level like evaluation, and also the user level evaluation. So it has a lot of success metrics when to meet. That are the things that ensure that your system is reliable and also accurate and have high quality reaction beyond demo.
Yeah, I think I can also add up a bit here. So for both the two questions, so I think it actually, so my opinion is actually quite like self-evident just based on my talk today. So first, for memory, I think memory should not be a narrow term just for the external memory. it's a broad term. It basically, as I mentioned, model weights is also a type of memory. Memory is a fundamental for learning, right? It's kind of like a unified view of like learning as evolution memory. So that's the first thing. Regarding the second thing, like reliability, actually that's is also kind of like core thing our company like targeted. And also I have already discussed this briefly in my talk today. So I think in one sentence, to achieve better reliability, we definitely need to put memory into the execution loop instead of just putting memory in the prompt. That's a core difference here. Right? You can imagine if the memory is just a prompt, then it still relies on the LLM to do the multi-step decision making, which you can never guarantee reliability there. Even the LLM is much better than today. But if you actually make the memory into something more predictable, more deterministic execution, then you execute it for 100 times, you get the same results every time. That's the reliability in my mind. Yeah. And also probably, I think Dr. Lee want to add something like verifiability. Like when the agent fail, it should understand it fails, right? That's also one type of like reliability.
Yeah. What I want to say is both are open problems. Maybe we want to say more, right? Yeah.
Just one more thing I would like to add for the reliability. So the goal for the reliability basically is to make the agent usable, right? So up to this point, I know someone you might read about a report from MIT Media Lab about the state of the AI in the enterprise. And right now, the success rate for the AI initiative is less than 5%. So there's still a long way to go. And definitely reliability is one of the key component for the agent to be usable in the enterprise environment. But also there are some other dimensions in this picture. For example, the accuracy, the precision. In some application space, like the medical application or financial application or legal application, definitely the accuracy or the recall for the agent will be the very basic requirement. Of course, the same thing with the security issue, and also the scalability issue in the enterprise environment. So there's still a long way to go for the agent to be really applicable in the enterprise environment. And so we need to focus on on some foundational issue like the memory we discussed today. And definitely there are a lot of work need to be done.
Okay, thank you. Huge thanks again to all of you today for sharing your thoughts and great vision. I think that brings us to the end of today's session. So we'll share the replay and slides on our community channels. So stay connected and don't miss the next episode of the AI co-learning program. Thank you all. See you.
Thank you.
Thank you.
Thank you
very much.
Thank you.
Thank you.
Have a
Bye.
great day or great evening. Bye-bye.